Hello, my name's Peter Holte. I'm with the City of Redmond. I'm here today with Josh Van Wee, Project Manager for Osborn Consulting, and Matt Ray, who's a Strategic Partner Manager for Opti. We're a project team on a pilot project that we want to talk to you about that happened in Redmond using a technology called continuous monitoring and adaptive control. Josh, can I get the next slide, please? Today, we're going to talk to you a little bit about what the considerations were about what we're trying to do in Redmond. We want to introduce you to the technology and actually tell you how it works and what it's about. A little bit of information about the siting of the pilot projects that we have and some of the modeling we did to make those considerations. A little bit more information about how the system works and some of the practical considerations when running it. And finally, I'll come back and give you some details about the next steps of Redmond's pilot project. Next slide, please. So the City of Redmond has a watershed management plan that divides the city into 20 watersheds throughout the city. Monticello is a watershed in the upper northeast corner of Redmond. It's 345 acres, and it flows to Bear Creek. It's partly in Redmond and partly in King County. The red line you see there on the map is really defines those two jurisdictions. The watershed is a priority watershed, meaning it's in pretty good shape, as based on a benthic index of biotic integrity, or BIBI score. Just a reminder, BIBI score is a system in which you collect insects at a stream, you sort them out and look at their assemblage and diversity, and based on that, you assign a index that details kind of the overall health of the entire stream system. Very simply put, our watershed management plan is looking to create environmental improvements for environmental lift, and we'll measure that by using the BIBI scores. Next slide, please. So what we're trying to do in Monticello is really defined by the characteristics of the watershed and what's going on there. You can see, if you look at this map, you see a lot of gray. The watershed is pretty near built-out conditions. If you look up in the corner of the map, you'll see a picture of the residential developments in that watershed and what they typically look like. This area developed over time with newer and older developments. So the different types of stormwater facilities we have in the watershed were built to different standards and control water to a different degree. If you're going to look at this watershed and try to determine what the biggest issue in this watershed is, it's really alter hydrology due to development. There are some water quality issues, but this is really the issue that we're facing mostly, and that should come not as a surprise to anyone who's working in watersheds in and around the Puget Sound area. That means two things. One, it means flashy flows or high flows during the winter, too much water in the winter, and then during the summer, low base flows, too little water during the summer. This is a particular issue in the northern portion of the watershed and on the main stem. Next slide, please. So the real question is, well, what do we do to improve this conditions and create environmental lift in this area? And here's considerations that we're considering. One is that we know we want to reduce runoff and extend detention within the watershed. We also know that because this drains into Bear Creek and is on a hillside and had a lot of glacial activity in the past, it has till soils that don't infiltrate very well, so it's largely infeasible for infiltration. There's a lot of lack of space in this watershed. There's not a whole lot of area to move around in. If you look at the map here and you see that Curry Pond, for example, is one of the two ponds we used in this pilot project, you'll notice that the houses directly to the north of Curry Pond almost sit on top of the pond. The pond's almost in their backyard. That brings up another issue, and that is that these are very well-established watershed neighborhoods. And we don't think it's a good practice in Redmond to go in and try to disrupt people's neighborhoods and create a large degree of disruptions to address some of the hydrology issues. We don't think that is a strategy that will garner a lot of support for our water restoration efforts. As always, cost is in consideration, and so we have to think about how we're going to pay for these things, and there's too much work to be done and too little money, so we all know that issue. The solution that we're trying right now as a pilot project is an active control at two ponds, the Curry East Pond and the Whistler Ridge Pond. We're using the Opti CMAC project system, and the goal is to reduce pulse counts and erosive flows that are flowing to Bear Creek. And you're probably wondering now what an Opti system is, what a CMAC system is, and Matt is going to kind of fill you in on that.
Thank you, Peter. So a lot of the question around this type of pilot project is exactly how do we take these existing facilities and improve the hydrology and increase these BI scores and lower these flow duration control curves. And Opti is a software platform solution that sits up in the cloud, and it's part of what we're calling a smart watershed. And this site level analysis that we'll talk about today is one piece of these smart watersheds. And so you see on the bottom right is the controlled pond, but we also have other ingestible sensors like water quality data and downstream and upstream data ingested into a software cloud platform that looks at precipitation forecasts from the National Weather Service and other providers, runs those through some background hydraulic modeling and watershed information that's already within the system, and then makes decisions on how to optimize flows out of those facilities based on that future data through these web dashboards. So next slide, Josh. And how this works on a site scale, not from a watershed scale, but at the individual basin scale, is kind of shown in this graphic here, where we take one of these older ponds that was developed under previous kind of design standards, and we retrofit the passive outfall. And these passive outfalls will have 1 to 2 orifices and some overflows, and they will have been primarily sized for flood control and some sort of water quality benefit. So what we do is we take those existing outfalls and we retrofit that with an actuated valve and a control panel that's connected to the Opti software via cellular connection. And level sensors within the facility read the level and understand the hydrology of that drainage area and what's coming up with the forecast and how much water is needed in storage to fully capture that storm event, and actuates that valve to release flow at a minimum rate so that it protects the downstream water resources and streams and those receiving waters. And so this creates an adaptive storage volume within that facility between the valve invert to kind of the first overflow perspective. Next slide. And so this is how this logic works and how the system actually interprets kind of the day of a storm event. So we have different states, which starts at dry weather, which is kind of your passive state. You could have a permanent pool, or this can be on a dry facility as well. And during that forecast period, when the system sees that there is a storm event coming, it runs through an analysis. There are over 1,400 individual control decisions that are run each individual day. So in these 5-minute increments, the algorithms are running and making decisions on how that facility should operate. And in that forecast period, if there needs to be additional volume in the facility and there's the ability to draw the permanent pool down, it will do so to create this storage. And then the valve will close during wet weather, as the majority of storms can be entirely captured within these facilities' storage volumes because they were designed for flood. And then in post-event, we'll hold for a specific period of time and then draw down at a low preset flow rate. Next slide. And so we also have a setting here, and this is important for flow duration control and hydromodification, which is what happens if the storm event is large enough that it's going to overflow or we need additional storage during that storm event. So what we do there is we have a setting called drain while rain, which allows that valve to be actuated and open during wet weather. And again, we look at the forecast in these different bins throughout time and figure out at what flow rate do I need to release this water so that at the end of the storm event, we're at the target elevation. And so we will minimally open that valve, and this is where you'll see the dramatic impact of a passive versus an active system by being able to minimally discharge during these events and always having this forecast information to know where the perfect amount of storage is with a degree of safety built into all of these things. And typically on our systems that we've installed with this logic, we see pulse counts reduced by greater than 75%, and all of the flashiness metrics like rate of rise, rate of fall, and by over 50%, and equivalent to about doubling the passive storage capacity of the facility. And so that I'll get back to some of the actual practical implementations and how we put these in the field after Josh goes through kind of how we ran through the Redmond projects to see what would be the most beneficial. So I'll turn it over to Josh.
Yep, thanks, Matt. So I'll talk a little bit about our site selection and modeling process. We started with 4 sites in the Monticello Basin. You can see the 4 sites here on this map. And we wanted to analyze them by this criteria here. So we wanted to look mainly at ponds that were built under previous stormwater standards. That's where we expected to see the biggest level of improvement. We wanted to do modeling to assess the improvement or the expected improvement that we could get at each location. We wanted to look at cost, so any variations in costs between the installations, and then neighborhood impacts. For our modeling approach, we were following Western Washington guidelines. So we were looking at flow durations and using WWHM to come up with the hydrology. So flow durations is essentially looking at matching pre-developed hydrology in a forested condition or getting things as close as possible to that condition with this retrofit pilot project. We took the hydrology results from the Western Washington hydrology model and plug those into a CMAC spreadsheet that Opti has developed. So that spreadsheet models some of the control logic and helps to model the improvements that you would get after installing the active control on the outlet structure of these ponds. That process and Opti's technology is approved by Ecology. It has TAPE approval and is functionally equivalent to a standard outfall structure. So it can be used as a retrofit or as a new installation to any type of detention, retention pond, water quality pond, things like that. Within the CMAC modeling spreadsheet, we set up several different targets. Our key targets that we were going for were the maximum water surface elevation. So really trying to utilize the full volume of the existing ponds. And then the target release rate. So we wanted to set a release rate that was low enough to where we would not be seeing those flows that are flashy or counted as a high pulse that are going to impact the stream health. So I'll talk through a couple examples, two examples of our results. So the first one that we'll look at is the Whistler Ridge Pond. We had positive results at this pond. This is a graph of the flow durations for the different scenarios that we modeled. So we're looking at flow versus the duration that flow was exceeded during a long-term simulation. So just kind of talking through these, starting with the blue curve on here, that's pre-developed conditions. So that represents the hydrology in undeveloped forested conditions. That would be what we would be going for if we were to meet the current flow control standards. On the right side, the red developed unmitigated would be if there was no flow control, flow just coming straight off of the developed neighborhoods and going into the creek. Then the yellow is existing conditions. So that's performance with the existing pond, the existing outlet structure. So you can see it's doing better than obviously if it was just coming straight off of the developed sites into the pond, but it's not meeting those pre-developed forested conditions that it would be required to under the current standards. So then with our CMAC mitigated scenario, we were able to bring the flow durations a lot closer to being in line with pre-developed. For the low end or for the lower flow rates, we were able to meet the pre-developed conditions. For the higher end, we were not able to meet that for all of the flows. Because this is a retrofit project, we want to get it as close as possible, but there are just limitations with the existing volume of the pond. So without expanding the footprint of the pond, it's not necessarily possible to meet all of the pre-developed flows. So then a second example, Fisher Village Pond. This is one where we saw kind of mixed results. So same color scheme here. The difference is that we did not see kind of that same across the board improvement between the existing conditions and the CMAC conditions. At the low flows, we saw a significant improvement, and then at the higher flows, they kind of tracked fairly close to each other between existing and the CMAC scenario. So some takeaways from our site selection process, just, as you saw from those last couple of graphs, the level of improvement varied. So it was pretty essential to do the modeling analysis and really look into what we would be getting from each pond. The intention was to select the 2 best ponds out of these 4 ponds to move forward with pilot projects. So we were definitely able to use the modeling to identify where we would get the maximum benefits. For our cost analysis, the costs all came out to be fairly similar between the 4 sites that we looked at. And that's just because each retrofit was a fairly similar configuration of a new actuated valve, outfall structure, and then the communications CMAC pieces. So the cost was not as big of a factor as the improvements that we would get at each site. But compared to other options, the cost was significantly less. If you were to look at expanding one of these ponds to a larger footprint, you would be looking at probably purchasing additional properties, expanding the pond, and that would quickly ramp up the price to probably an order of magnitude higher than doing one of these retrofit projects. And then just looking at the neighborhood factor, these were pretty relatively simple from the construction standpoint. They were installed within a 2-week to a 1-month type of time frame. There's not significant neighborhood impacts as far as construction or needing to expand and construct in a large area. So that was definitely a benefit for moving forward with these. So from there, I'll pass it back to Matt. He'll talk a little bit about the installation and optimization.
Thanks, Josh. So this kind of falls into that neighborhood disruption and cost analysis piece, where we're taking an existing facility and making a simple retrofit to increase the performance. These are the actual installation photos from one of the 2 ponds. And what you see in the center here is the existing outfall structure being retrofit with a flange to put the actuated valve on. The picture on the left is that actuated valve, or is the actuator above ground, and the entire control system is solar powered on the right there, and it's a concrete pole. So the entirety of the project is some conduit runs and some installation, electromechanical installation costs to get these things mounted and put together. Next slide. So a lot of what happens after we put these projects in the ground is an optimization period, which is a 3-month phase following installation of the equipment, where everyone knows you model these things and you have assumptions based on the hydrology and how that watershed will respond and how that pond works. But reality is often different than modeling. And so what we do is we have this optimization phase where we run storms, or we don't run storms, we analyze storms that go through these facilities for that duration and optimize the settings, change the configuration factors. There's over 80 different individual settings that can be changed within the software logic to create an ideal kind of configuration for that individual pond. And so after we look at these settings over that period of time, run it back through an analysis to make sure that it's would have operated throughout the continuous simulation of the long term effectively. And then we essentially turn that project into an automatic control where the system makes its own decisions with Opti staff in the background checking them on multiple times per week to make sure they're operating properly. Next slide. And what this looks like from the user's perspective is this is an individual dashboard for a particular site, and this is what you would look when you logged into the Opti software, which from any web device. And so you have a control pod in the top left corner, which is where the user, Redmond in this case, can take control of their facility and turn it from automatic to manual control if they want to do maintenance or they want to draw the system down or want to for any type of use to turn it off of automatic control. And then you'll have your storm status. You'll see what's predicted in the forecast from a volumetric standpoint. And then you have your sensor data, which is the level within your storage and your outflow valve state. You can see what the valve is doing, what it's going to do, what its target states are, how much water is in the system and how much water is predicted to come in, and kind of what needs to happen during that next phase. And then you have multiple tools that allow you to navigate different time periods and get historic data downloaded at any time. All of this data is cloud stored and available 24/7 throughout the entire life cycle of your project. And so with that, I will turn it back over to Peter, and I think we'll wrap it up and start taking some questions.
So next steps and where we're going with the pilot project that Redmond's running. Well, one thing is that we've done some kind of back of the envelope calculations on the cost of this technology versus the alternatives, and it looks pretty good. It looks really, really good, but I want to do a more in-depth analysis on that. We want to monitor this program, and the great thing about this system is that we'll have continuous monitoring. It will tell us exactly what's happening to the pond at any one time. Monticello is part of the Stormwater Action Monitoring Plan Shared Watershed, Paired Watershed Study. There was a presentation on that yesterday, so if you want to go back and look at the recording on that, I encourage you to do so. But it's a study to look at different techniques and different treatments that are being taken in watersheds to see what's working. So we will be using the Paired Watershed Study to monitor this project and see how well we're doing. As part of that, we'll be looking for additional places to put CMAC installations. Right now, these two installations will treat about 10% of the watershed. We'd like to get up to about 20–25% because we think that will help us understand better how this technology is working and meeting our goals. I think there's a good story to be told here, so I would actually like to do some outreach on this. The people who live in the Monticello watershed, a lot of them work in tech companies, a lot of them work for Microsoft, and we don't do a lot of innovative activities in watershed management. And here's a case where we're doing innovative with technology, and I want to see if we can use that technology angle as a hook to kind of get some of these folks who live in the watershed interested in restoration activities more in general. As far as permit compliance, this watershed, Monticello, will be our Stormwater Management Action Plan watershed, our SMAP watershed, to meet our NPDES requirements. But I also think in terms of the phase ones and the structural control requirements that they have coming in the current permit, and think that they might be facing some of the same issues that we were facing in Monticello, and this might be a good tool to help them address some of those issues. So I was thinking about you folks when I looked at this technology. Lastly, as I said, we will have lots of data telling us how well this technology is working. We will also be able to adapt it over time if it's not working exactly how we'd like to, which is really exciting. And I hope to bring back that information to the stormwater community in a lunch and learn or some other methodology to tell you how it's working and kind of share some of that data with you. And with that, next slide, we can take questions. And as I said, if you want to contact any of us, you can. Or if we find there's a great deal of interest, you can go ahead and contact me, and I will set something up, and we can have a conversation just at a later date to kind of discuss some of the questions that you'll be bringing forward.
Great. We've got quite a few questions in the chat box. The first one, and we've got about 7 minutes for questions. So the first one is, why don't you think the Fisher Village Pond got much better results than the existing conditions?
Yeah, I think that's a great question. It has to do with the outfall structure and then the contributing basin hydrology. And that is one of our next steps with the city, is to dive into that a little bit more. But we did see, just depending on whether it was a 3-orifice structure versus a notched weir, and then I think just depending on the specific stormwater standard that it was designed to, and the volume of the pond under the previous design standards.
Yeah, some of the hydrology around these facilities, if they're undersized in their current condition, the ability to uplift is limited. Some of them have more storage, just even if they sometimes were over engineered or had more storage than was originally intended. So that's where you see the benefit is, especially the older ones that are more of flood control benefit have a greater delta. But so, yeah, and what Josh has said, we have seen some projects that have smaller, very small existing orifices have less of an impact from a CMAC retrofit.
And the next question was, any of this work subject to HPA, or were all these stormwater only facilities?
They were all stormwater facilities. They're all, both of them were detention ponds, and the extensions we will do will also be detention ponds.
Is there a downstream hydrology station in the receiving water where stage data is being collected to see if high pulse counts are being reduced?
Yeah, that's actually part of the paired watershed study and was part of our consideration when we cited, when we were talking about which ponds to choose. I mean, it was really come down which ponds are going to work, but the initial looking suite of ponds that we looked at, we also looked at where we had some data and whatnot. So as part of the paired watershed study, we're hoping that we can link the outcomes at the pond to what's going on in the actual stream. That's kind of the gold standard right there.
Is there a pond size or contributing area that provided favorable for these retrofits? Any minimum or maximum thresholds to those two metrics that you would recommend?
Josh, I don't know if I don't exactly remember the contributing areas to those facilities, but it's almost universal in that the larger the drainage area and the larger the facility, the better the performance. I don't know of there's really no maximum threshold, but minimum thresholds are really around pond size, and we typically like to see ponds that have more than an acre or a half of an acre of surface area. That's just been my kind of experience throughout the last 6 years.
Yeah, and I agree. I think the larger area, more volume to work with, allows you more flexibility in your active controls.
Does controlling the outfall orifice help at all with maintenance needs of ponds, i.e. reducing need for removing sediment?
It's an interesting question. It actually, so Opti's, so the technology, by increasing residence time and increasing storage within a facility, you typically, and you actually will have more sedimentation within a facility because you have a much longer holding time. So in one hand, we do increase the maintenance visibility for a facility because you have real-time data and continuous alerting that says, hey, this facility is either not draining appropriately or is draining too fast. But from the need of reducing a need for removing sediment is not one of the benefits of CMAC.
Okay, so we've got just a little less than 2 minutes now. Let's see. So what brand of valve was used in the study? Did the valves replace the control structure installed in the existing condition, or is it combined with a control structure?
They are Rotork valves, and they do not replace the control structure, but the control structure is often modified by plugging smaller orifices and coring a new, larger 6 or 8 inch, all the way to 18 inch or even slide gates to control that. And that's all part of the engineering design process to figure out which existing orifices need to be plugged and how we want to size it, because that's part of the hydrology modeling.
And in this case, we were able to remove the existing risers from both ponds, so everything is controlled by the active valve.
So one last question. What was the review process through ecology for CMAC functional equivalency determination?
So that was done through another consulting firm. Geosyntech Consultants worked with us over a year to develop the modeling and the spreadsheet tool. And we worked with Doug Howie and his team to go through those results and iterate and to understand how that model worked and how the technology worked. And yeah, so over that year process was just developing of the modeling and back and forth till we got to approval.
Awesome. Well, that's all we have time for. Thank you very much for a great presentation. And thank you for all your questions to the attendees.
Thanks.
Thank you.